Okay, so this is a second problem, and I kind of highlight the Kc value. This one is almost like 500,000, right? So this is a case where you are seeing the Kc value is big, and it gives you a very important clue. So what's the Kc? Let me go back to the original. Kc is, I guess, a reactant concentration and product concentration. I put a quote unquote, but this is not exact, but in general it's a ratio between product divided by reactant, and it is one over the other. And if you look at the Kc value is really large, okay? Something like 10 to the 5th. What I mean is you have a 1, the top is like 0.1 million. So there is a lot of products at the end, but with the expense of having a small amount of the reactants. So that's the meaning of these two. And then let's look at the problem. Okay, so this is an equation, and this is what we call the formic acid. You don't have to know the name. Formic acid. This formic acid decomposes into the carbon monoxide and the water, and then they say, okay, I put this formic acid 0.2 moles in 1 liter. So 0.2 big M molar concentration. And what will be the concentration of CO2, CO, and then H2O? And actually, I also add a new question on what will be the concentration of formic acid and equilibrium. So this is the one. And they even wanted to make sure this K value is very, very large, and this is trying to give you a clue. So when Kc is, I guess, really large, I don't know what really large means, but it's a really large. It's not a 1, and you can assume all the reactants are neutral. So that will be some clue that I want to have, because what you see here is that this is a reactant, and they give you an initial concentration, which is, I guess that concentration is 0.2 big M. But because once you have put this one, because of large K constant, everything is turned into 0.2 moles of CO and 0.2 moles of H2O. So I am going to write this equation HCO2H going back and forth CO. This is always comes in handy to redefine what will be my initial, what will be my change, and what will be my equilibrium. I like to draw this line. And among all these I's, the most important one is obviously the equilibrium. That's what we are going to focus on. So although this is my initial concentration, I'm going to say everything is converted. So it reaches total conversion of those two products. That is my first, I guess, second generation of initial condition. Okay? So you put this, but everything is changed to the product, and then you're going to dial back. Okay? Dial back a little bit. What will be how much of this product? This is cannot be happening because the equilibrium constant still there's a small little bit of something left. So first you have 100% conversion, and then you're going to say you're going to lose some and generate this one back to certain concentration. So what I'm saying is, okay, I'm going to lose some now. I want to generate X. So that is kind of the logical ways to solve this one in a very easier way. And then what you have is, if you add them together, that will be an X. There will be a 0.2 minus X, 0.2 minus X. And I think that is also to know that X is very small. Okay? very small. So remember that x is a very small number. And then I need to write this Kc as an expression. So Kc, which is now H, formic acid concentration, and CO concentration, H2O concentration. So this is a definition, and at equilibrium, so this is a x 0.2 minus x to the square. Okay, so up to here, everyone can do that. Okay, up to here, even this is a mathematically defined one, but now you have to use your insight to approximate. This is the key of the chemistry portion, because I know you will see that a lot of courses down the road in your college classes, there's a nice approximation, makes your life easy. This is an ugly term, right? This is a quadratic term, but I know 0.2 minus x is not so different from 0.2, since x is very small. People like to use this, neglected this term, because I use an expression that, okay, I have a $1 billion in my bank account and somebody steal $1 from me. How much money do I have? $1 billion, right? So it is the same idea that although it is mathematically defined, it is not meaningful, so that my life is easy now. Because now this equation, all of a sudden, that probably the equation that you used to see in your elementary school, right? Right. What's the number now? Now still I have to deal with, I guess you don't see the big numbers in your elementary school, but that's the one, right? So can you solve this? Very easy, right? So by having this approximation, knowing that x is very small compared to what you have given, and then this is a simple number, and then it will be just a simple linear or first order equation. And then x is, therefore, is 9.3 10 to the minus 8. And which is, if you look at that, x is this, which is a concentration HCO2H. People put equilibrium, so that's an equilibrium concentration. So that was a question here, but they also say what is a concentration of CO and H2O, which is to me, the very simple and not so meaningful question. What is the question on this? That will be this, 0.2 minus x, and we already all know that that is close to 0.2. The answer for this is 0.2 for the first two questions, because that's a 0.2 minus x is the same as 0.2. The x, which is a reactant concentration at the equilibrium, will be this very small. Right? It's like, once again, it's like a 1 over billion. Right? This was small. So this is once again, now this is a case where you are seeing K value is really big, then you know the products of a lot, and then there is an easier way to solve this one and just